What's up? My name is Matthew, and in the next series of videos, we're going to talk about complex numbers in the polar plane. And I think I have this video chopped up into 4 segments. That's my plan anyway. We'll start out looking at what it looks like and what the sort of process looks like for taking a complex number and converting it into polar form, and we'll plot a couple of points. And then we're going to look at multiplication and division of complex numbers in polar form. And then we will look at taking a complex number in polar form and raising it to a power. And then I'm saving the best for last. I'm going to show you how to take an nth root, like a square root, cube root, fourth root, and so on, of a complex number in polar form, and that's the one that's going to be a little bit of a brain stretch. So let's get started. And the first thing we need to talk about is sort of the shape of a complex number in polar form. And I'm trying to find me. There I am. We've now, in the course that I'm teaching, which is a Precalc course, talked about a lot of things that are on the rectangular coordinate plane, the normal xy plane, and then just recently we were talking about the polar plane and plotting polar points and graphs and equations and things like that on the polar plane. And now here we find ourselves on the complex plane. And the complex plane is using the same xy coordinates, which have, when you first started learning about plotting points on the Cartesian coordinate plane, the x and the y were kind of arbitrary. They didn't have a specific value or units associated with them. And then as we've progressed through our math education, we found that you can represent or use the x-axis to represent things like time. So as time is progressing from left to right, on the vertical axis, something might change, like the height of a projectile, or the value of an investment, or the distance away from a starting point, or something like that. In our conversation in this video, the x-axis is going to represent a quantity of real stuff. It's going to represent a real value, a real number. We're not necessarily going to put units on it, but the x-axis is going to be our real axis, and the vertical axis is going to represent how much imaginary stuff we have. So we've got real and imaginary, and when you take those two things and put them together, they become quite complex. And so we say that a number that has a real component being added or subtracted with an imaginary component is called a complex number, and we usually represent that in what's often called standard form, a+bi. And right at the bottom of your screen, you're seeing in a blue box, we're talking about the absolute value there, but at the very bottom you see the absolute value of z equals the absolute value of a+bi. And a+bi, again, is a complex number written in standard form. And so let's just keep going talking about the absolute value of a complex number. Z is very often going to be the letter that we use to represent a complex number. And when you take the absolute value of it, that's the same thing as taking the absolute value of a+bi. So that's a more specific representation of that complex number, z. And to do that, we take what looks like the distance formula. We're doing the square root of a squared plus b squared. And for the moment, let's just stick with that and go into example 1 in this blue rectangle toward the top right corner of the screen. And let's take the absolute value of z, which means we need to take the absolute value of 3 minus 4i. And this sort of formula at the bottom of the screen is telling us that that's equal to the square root of -3 squared plus, in this case, -4 is our b value, and we have to square that also. That ends up being the square root of 9 plus 16, which is the square root of 25, which is equal to 5. So what really is the purpose, I suppose? I don't know if I want to talk about purpose. That could get pretty philosophical. But I can show you that visually, the 5 that we just calculated is, speaking of the distance formula, is the distance of that complex number plotted as a point on the complex plane. It's the distance from the origin to that point is equal to 5. The value of it, the purpose of it, I don't think we're there yet. Maybe a couple more years worth of math and you could really dig deep into what the actual purpose of that is. But for the moment, if you're asked to find the absolute value of a complex number, that's how you're going to do it. So polar form of a complex number, so we're sticking with the polar plane and sort of combining it with the complex plane, we see again that we have z representing a complex number, a plus bi, and we can represent this like an x coordinate. This a value is going to be r cosine theta. The b value, like a y coordinate, is r sine theta. And that multiple of I, which makes that the imaginary term, does come along with us. And after making this new representation of a complex number in what we're calling polar form, notice that each of these terms, this one and this one, both of those contain a factor of r. So we could factor out the r and write our polar form of our complex number as r times the quantity cosine theta plus I sine theta. Sometimes this is written as sort of a little shorthand notation. Sometimes we write r cis theta. So that's r cosine I sine theta. I might use that, so I want you to see it. I don't know that that's common practice or sort of a standard way to write that, but it is a shorthand notation that I have seen in other places, so I wanted to make you aware of it. Especially when we get to the very last segment of this conversation, we're going to be writing cosine plus I sine theta over and over and over again, so the r cis theta might come in handy. All right, so you're seeing another graphical representation of our complex number, z equals a plus bi. You're seeing the theta value in that diagram. You're seeing the r value in the diagram. The r, again, is equal to the absolute value of z. The radius is equal to the absolute value of z. We saw that at the top of this page. All right, so this is a very detailed and formal description of the different components of our complex number expressed in polar form. Z equals r cosine theta plus I sine theta. You see the a value, as I mentioned earlier, is equal to r cosine theta. B is r sine theta. We just saw in a second diagram that r is equal to the square root of a squared plus b squared, otherwise known as the absolute value of our complex number. And tangent of theta is still equal to b over a, because that's like taking our y value and dividing it by the x value. And we've seen that occur in the previous videos where we were working with equations and the polar plane. So let's go through a couple examples here and see about how to write each of these complex numbers in polar form. The first thing that I do in a problem like this is to rewrite this in the form of a plus bi, which would be 0 minus 3i. So now I know that my a value is a 0 and my b value is a negative 3. Great. How do I write this in polar form again? What's my destination? Oh yes, z equals r cosine theta plus I sine theta. So to write this number in polar form, we need the r value and we need our theta value. This particular problem lends itself very well to drawing a quick diagram. So I'm going to draw a little arrow over here and I'm going to plot this point on the complex plane. So remember that the horizontal axis is your imaginary axis, or sorry, is your real axis, and your vertical axis is your imaginary axis. So we're not moving at all. The 0 represents motion in the horizontal or real direction. The -3 tells us how far we're moving in the imaginary direction or the vertical direction. So the point that we're going to plot is actually down here. Now remember, we need an r value and a theta value. R represents how far we are away from the pole or the origin. So in this particular case, I think it's fairly obvious that our r value is equal to 3. And I think it's also fairly obvious that our theta value is equal to 270 degrees or 3 pi over 2. That pen was a little aggressive for me. Let's dial it down. There we go. 3 pi over 2. Wherever you want to put that diagram on your paper. So I'm actually going to wrap this problem up and say that -3i as a complex number is equal to 3 times, so that 3 is my r value, and if you want you could write r cosine theta plus I sine theta to give you sort of a framework, and then you can kind of fill in the blanks. The 3 is the r value, cosine, and then whether you want to use radians or degrees, I'm going to go with radians, cosine 3 pi over 2 plus I times the sine also of 3 pi over 2. That angle measure is always going to be the same in both positions. And it's pretty typical to write the I before the sine. I wouldn't put the I at the end, which is a little irritating because normally we think of this as a plus bi, and the I normally comes at the end, but here we're going to write that I as a coefficient on the sine function. All right, so what we didn't do here is we didn't calculate the r value using the formula, square root of a squared plus b squared. We also did not use the idea of b over a, or rather the tangent of theta equaling b over a. So let's go into this next problem and use that more typical approach, but as you might well know, I'm a big fan of drawing a diagram. That helps me get right answers. Hopefully that helps clarify some things for you also. All right, so let's go traditional on this one. R is equal to the square root of a squared plus b squared, which is equal to the square root of -2 squared plus 2 root 3 squared, which is equal to the square root of 4 plus 12, which is equal to the square root of 16, which is equal to 4. So that's our r value, and the tangent of theta is equal to b over a here. Tangent of theta is equal to 2 root 3 over -2, which is equal to, if we simplify that fraction, that's equal to -√3. The 2 over the -2 turns into a -1 times the rad 3. So that's equal to, well, oh boy. So the tangent of theta is equal to -√3. Is that even possible? Yes, because the range of the tangent function goes from -infinity to +infinity. Now how am I supposed to solve for theta? We're going to take the inverse tan of both sides of this equation. So I'll draw my next arrow down here and write that theta is equal to the inverse tan of -√3. I tried to make that look like a 3, I just made it look worse. Ugh. There we go. Okay, let's jump into our calculator, which I have to grab mine, and see what technology tells us. I'm going to stick with my scientific calculator because my students are going to be using only a scientific calculator on their next exam. And I will type in, well, first of all, I'm going to make sure that I'm in degree mode. I want to see my answer come back in degree mode, and for some reason I also see the word stat on my screen. I don't know that I've ever seen that before, and I'm pretty sure I don't know how to get rid of it. I'm looking for stat somewhere else on my keypad. I don't see it. All right, hopefully that doesn't mess things up. Now, I'm going to type in 3. I'm going to hit the square root button. And then down near the equal sign in the bottom right corner on my scientific calculator, I see a plus minus button. So I'm going to hit that. That switches the sign. So now on my screen, I see negative 1.732050808. I'm going to take the inverse tangent of that. So I'm going to hit the second button in the top left corner of my TI-30XA, and then I'll hit the tangent button in order to take the inverse tan, and I got an answer of negative 60. So that is telling me that theta is equal to negative 60 degrees, or negative pi over 3 radians. Anytime I take or use an inverse trig function, I'm always a little bit nervous because I know that each of the 3 basic trig functions in their inverse form are only capable of returning angle measures to me in 2 out of the 4 quadrants. What if I need my angle measure to be in one of the other 2 quadrants? Then I'm going to have to do just a little bit of arithmetic. That part's easy, but making the determination, or remembering to make the determination, to do that little double check to see, now which quadrant's theta really supposed to be in, I think that's the part that requires the most discipline. Trying to remember to double check. So now I'm going to draw out my little diagram. The complex number that I'm working with is negative 2 plus 2 root 3. So negative 2 is my a value, or my real value, or my x value, or my a value. Yikes. But it's my horizontal value. So I'm moving to the left 2 units, 1, 2, and then in the vertical direction 2 root 3. So 2 root 3 is just a little bit more than, or just a little bit less than 3.5, right? It's 1.7 times 2, which is 3.4. So I'm going up 1, 2, 3, 4, roughly 4. Or sorry, 3.4, so a little less than 3.5. Here is my r value, right, from the point to the origin. I don't know why I've drawn this diagram so small. There's r. Actually, let me put it down here. And this is my theta value. Does that theta value look like negative 60 degrees to you? It doesn't look like negative 60 to me. Negative 60 to me should be pretty far down in the 4th quadrant. We're pretty high in the 2nd quadrant. In order to make that sort of transformation, or to swing us into the correct quadrant, we need to take the angle measure of negative 60 degrees and add 180 degrees to it. In a previous video, I wrote some notes that talked about what you should do if you use the inverse tan function and your actual destination is the 2nd or 3rd quadrant, but you use the inverse tan and it returns an angle measure that's in the 1st or 4th quadrant. And I said previously to add pi over 2, and I misspoke. You really need to add pi, or 180 degrees, a half of a rotation, in order to correct the angle measure. So that's what we're going to do here. We're going to add 180 degrees. And I apologize for that previous error. I try to keep my errors to a minimum, but it does happen. So let's put maybe just one more arrow underneath here and say that theta really needs to equal negative 60 degrees, which is in quadrant 4, plus 180 degrees, which equals 120 degrees, which is correctly in quadrant 2. Nice. So we have our r value of 4, we have our correct theta value of 120 degrees, and we can finally write our complex number in polar form. -2 plus 2 root 3i is equal to r cosine theta plus I sine theta, which is equal to 4 times the cosine of 120 degrees, or 2 pi over 3 radians, 2 pi over 3 radians, plus I times the sine of 120 degrees. All right, there you go. That was a good one. This is a particularly good problem because it contains the issue with the inverse tan function returning the wrong angle measure. So I'm glad that we got to see that variation. In this problem, we also used the sort of more formal process of calculating our r value and the theta value using the tangent or inverse tangent function. This problem, you could follow the exact same process. What I will tell you is that your r value is going to be negative square root of 6, because a squared plus b squared is 1 plus 5, which makes 6. Then you square root that, so your r value is going to be the square root of 6. Your point is in the fourth quadrant, which is helpful because when you use the inverse tan function to get your theta value is going to be correct. It's going to be a negative theta value, but it is going to be aiming you in the correct direction and into the correct quadrant. If you need to answer with a positive angle measure, please make sure to add 360 degrees to swing you from the fourth quadrant all the way around and back into the fourth quadrant, or add 2 pi radians, and don't forget to round appropriately depending on the call of the question that you're working on. All right, that is the end of the first segment of this conversation. If you are ready to move into the next section, please click on the little window that is below me, and that will take you into our next segment and conversation, which is about multiplying and dividing complex numbers. See you there.